Hello friends, I am Nihal Rajpal. In this series of videos, we are going to see the implementation of Mano machine. So Mano machine is the basic computer which is defined by Mr. Maurice Mano in the chapter 5th of his book Computer System Architecture. So we have tried to implement that in the Logism simulator, which is the free and open source digital gate simulator. So before directly jumping to Logism, let's quickly see the system specification. Starting from the bottom right, we have AC, which is your accumulator. So it accumulates all the result of the ALU and also forms the first operand for all the arithmetic and logic operation. Then we have DR, which is your data register. So it forms the second operand for the ALU. And whenever the data is fetched from the memory, DR is the register which receives that data. Then we have TR, which is simply temporary register, and it is not used much. Then we have IR, which is the instruction register. So it always contains the instruction which is currently being executed. So control unit always takes the instruction from the instruction register and generates the control signals accordingly. Now all of these registers were of 16 bits. Then we have 12-bit registers like PC and AR, which always contains the address. So PC is program counter, which contains the address of the next instruction to be executed. Then AR is the address register. It provides the address to the memory. So if the AR contains the value 100 and when the memory read operation is performed, then the data will be fetched from the location 100 because AR is provides that value. Then we have two 8-bit registers like input register and output register, which are used only for the IO. Now the memory used in this computer is of 4096 words. It means that we need at least 12 bits to uniquely identify those 4096 words, and each word in that memory is of 16 bits each. We have three types of instruction. If the bits 12 to 14 are not 1, then it is the memory reference instruction, and in that case the MSB actually decides whether it is direct memory reference or indirect memory reference. So if the MSB is 0, then it is direct memory reference instruction, and if the MSB is 1, then it is the indirect memory reference instruction. Now that was the case when 12 to 14 bits are not 1. If the bits 12 to 14 are all 1 and MSB is 0, then it is register reference instruction. And if MSB is 1 and 12 to 14 bits are also 1, then it is your IO instruction. So these are all the instructions which are supported by this computer. We have 7 memory reference instruction, 12 register reference instruction, and we have 6 IO instruction. So we have total of 25 instruction, and yes, all the instruction are actually implemented in Logisim, so we can execute any of them. So without discussing much, let's quickly see the implementation. Okay, so this is the final implementation. So we have created a separate module-based circuit for each and every component. As you can see on the left, we have a component for control unit, which generates all the control signals. Then we have a component for arithmetic and logic unit. Similarly, we have a component for all the registers. At the top, we have our memory, which has 4096 words. On the right, we have this common bus system. Then we do have some displays to display the value of the registers. On the right, we have some flags, and we are going to see the implementation of all the components in the upcoming videos. So as of now, let's see the working. So this is the test program which I have written for the demonstration. So the first instruction is your load accumulator. So it loads the accumulator from the location pointed by SRC. So as of now, SRC is pointing to location number 4. So 1127 will be fetched and loaded to the accumulator. Second instruction is the increment one. So it increments the accumulator. So 1127 will be incremented to 1128. Then third instruction is the store accumulator. So it stores the incremented value to the location pointed by DST. So as of now, DST points to the location number 5. So the incremented value that will be 1128 will be stored at the location number 5. And then finally, we have halt instruction to halt the execution. So after the execution, the content of the location 005 must be 1128. So let's load this program into Logisim. So the first one is our load instruction, which is 2004. Then we have increment, which is 7020. Then we have store, that is 3005, because we have to store at the location number 5. And finally, at location number 3, we have halt instruction, which is 7001. And at the location number 4, we have to store data, which is 1127. So to start the execution, we can manually supply the clocks from here. But in Logisim, we have an option of tick enabled under the simulate menu. So we will use this for automatic locks. Now, after the execution is complete, this red LED will turn to green and we can then stop the clocks. So let's start. So yeah, now because it has turned to green, we can actually stop the clocks. Now, if we see at the location number 005, it is 1128 and the location the value of PC is 4 because the last instruction was executed which was at location number 3. So while that was executing, the PC was already incremented to location number 4. Data register contains the value 1127 because 1127 was the last fetched data from the memory. Accumulator is 1128 because 1127 which was fetched was then incremented by the second instruction. IR contains 7001 because it was the last instruction which was executed and 7001 is our halt instruction. So yeah, that was all for this video. I hope you found this helpful and I will see you in the next part. Thank you.